Good afternoon, students. So, as we know, quantum mechanics was developed over 100 years. So, 100 years, 125 years old subject. And the first paper was published in the year 1900. And as we know, this is about black body radiation by Max Planck. And thereby, lot of papers have been published. So up to 1925, these papers they belong to elementary ideas. They said only elementary ideas. We call this as first quantum mechanics. So after 1925, Heisenberg put forth a lot of ideas and he developed matrix mechanics. So 1925, matrix mechanics was developed by Heisenberg, and the next year 1926, wave mechanics was developed by Schrödinger. So there are two avenues in quantum mechanics. One is about matrix mechanics and another one is about wave mechanics. And very next year 1927, Schrödinger himself proved that both the mechanics are equivalent. So both they represent the state of a vector, quantum states. And in fact, so 1930s, Paul Dirac from UK, he developed a lot of ideas and he wrote a book, The Principles of Quantum Mechanics. That was the first book in quantum mechanics, and people used as textbooks on this subject. And he developed a lot of ideas about Heisenberg matrix mechanics and Schrödinger wave mechanics into a single mathematical formalism. And in fact, he said these quantum states, they live in Gilbert space. So he is Gilbert. It's a mathematician. He belongs to German. And Newman also developed a lot of ideas in quantum mechanics. He wrote a book on mathematical foundations of quantum mechanics, 1932. And these three persons are very important. In fact, they developed mathematics. Mathematics is very important in quantum mechanics. So linear vector space is the subject today that we are going to learn today. And in fact, quantum mechanics lives in linear vector space. So we can say clearly, quantum mechanics lives in linear vector space. Any quantum state psi, physical state, this is a state vector, or any quantum particle will be represented in terms of psi. This psi lives in linear vector space. And of course, we know about the vector space very well. Vector space, which we have studied already, this is called the Euclidean space, and constants will be in terms of real numbers. So in vector space, constant will be real numbers. Whereas we are going to study that these constants, these coefficients, the probability amplitudes of psi, they belong to complex numbers in Gilbert space. So we have complex numbers, which is nothing but real part and imaginary part. So these complex numbers they live in linear vector space. So in real space, we have only real numbers. In linear vector space, we have complex numbers. Okay, so what is the meaning of linear? The operation. We are going to have some operations here. These operations will be done linearly. That is, one state to another state, if they transform, this transformation will be nothing but the linear transformation. The transformation will be linear. So that's why it is termed as linear vector space. Okay. And he developed Keck-Braun notation, which we are going to look into next slides. Okay. Keck-Braun notation. So Keck-Braun notation often will be used in matrix mechanics. Okay, so this is ordinary wave mechanics, and this is Keck-Braun notations. Okay, bracket notations. Now we are going to introduce Ket-Bra notation is very to represent any quantum state. Okay, for example, if you take psi, okay, it's a quantum state. Ket-Bra notation is nothing but this is a ket vector. You have one line and you have this okay, this bracket. Okay, this is called a ket vector, and this is called a bra vector. So bra vector and ket vector. This notation is called the ket vector. This notation is called a bra vector. If any quantum state, that can be represented in terms of a ket vector. Ket vector will be always a normal vector. Ket vector will be a normal vector, ordinary vector. We are going to take the complex conjugate of psi. So this is psi star, and you will have bra vectors. For every ket vector, there will be a bra vector. For every bra vector, there will be a ket vector. We call these two as dual space. Dual space. This dual space is nothing but a Gilbert space. So Gilbert space in which you can have real numbers as well as complex numbers. Of course, we know that complex number is nothing but real part and imaginary part. So in Gilbert space. And we know that the real space will be 3 dimensional. So we know already this is 1D, 2D and 3 dimension. Whereas in Gilbert space, this will have a n dimension. So n dimension space is nothing but a Gilbert space. So any quantum state is represented by an element whose basis exists in Gilbert space. We will talk about basis later. So as I said, this psi state vector in the complex vector space, for every psi there will be a bra, for every bra there will be a ket, and this space is nothing but Gilbert space. The dual conjugate of ket is bra, and for bra it is ket. So for example, if you take A psi, A is a scalar. If you take A psi, I can pull A out. Okay, it's a constant. I can pull out. A can be either real number or a complex number. Okay, so I can pull A out. So I can write this expression as like this. So this is for the ket notation. When you are going for the bra notation, so bra notation, A psi is here. Of course, this is psi is nothing but a complex number, complex of psi. Correct? So this is in A. This is if I take this one out, it becomes a A star, complex number. Okay, this is a complex number. So this must be a real number. This must be a complex number. Is it okay? Similarly, you can use this notation A psi star. A psi star can be written as A star psi. Okay, A psi whole star, that will be A star psi. Is it okay? What times? You have A psi, that is ket A psi whole star. So if you take out this one, will give you A star, and psi ket psi of a complex conjugate, that will give you bra psi. So we can write bra psi. Is it clear? Okay. So now we are going to matrix representation of bra and ket vectors. So as I told you already, bra and ket notations are very important in matrix mechanics. Just now I said. So any ket vector can be represented in terms of a column vector. So all ket vectors will be represented in terms of column vectors. It's like for example psi, which consists of many elements. So psi 1, psi 2, dot dot dot, psi n. So similarly, any bra vector can be represented in terms of a row vector. So we have a small mnemonic. So here bra r is there. In row vector r is there. So we can say we have just a mnemonic. So any bra vector will be represented in terms of row vectors. Okay. So phi consists of many elements. So phi 1 star, comma phi 2 star, dot dot dot, phi n star. Suppose if you have two vectors, phi and psi, then the scalar product of two functions, and of course scalar product is very very important one. Scalar product is nothing but, as we know already in mathematics, I dot I, j dot j, k dot k equals 1. So they are all scalar products. I dot j, I dot k will be 0. So two operations are necessary. One is I dot I, that will be normalized. I dot j equals 0 is orthogonal. Okay, so orthogonal and normalization, these two properties are very important. So in Gilbert space, the inner product should be defined. So earlier I said Gilbert space in which we have two main things, two properties. One is dual space, another one is inner product. Dual space. For every bra vector there will be a ket vector. For every ket vector there will be a bra vector. So this is very important. Also in Gilbert space there will be n dimension one. It is not 3 dimension. It is n dimension. Second one. And third one will be inner product. Inner product should be defined. Only then we can express all the elements in terms of Gilbert space. Suppose if we take this ket and bra. So we have ket and bra. So we have ket psi sandwiched with bra phi. Okay, this is bra phi. This is ket psi. Okay, what we call this as inner product. So this is nothing but a overlapping. Inner product is sometimes we call this as overlapping. So this bra will be always associated with complex conjugate, correct? So we can write this as in terms of wave mechanics as phi star psi d tau. D tau stands for volume element. D tau equals dx dy dz. In some other book you may find dv equals dx dy dz. Some other book. So this is volume element. Now I can interchange. I can change ket into bra into ket, taking the complex conjugate. Okay, taking the complex conjugate. Correct? Ket and bra can be written in terms of like this. We will solve one small problem using inner product and a complex conjugate. Suppose if you have ket vector is 1, 2, 3. Okay, your ket vector psi 1 is this one, psi 2 is this one, 1, 1, 2y. So we are going to calculate psi 1, psi 2, inner product of ket psi 2 with bra psi 1. Okay, so psi 1, this is bra psi 1. So you have to change into bra psi 1. This one is ket psi 1. Okay, change into bra psi 1. So this is column vector. You change into row vector. So 1, 2, 3. This becomes 1, 2, 3. Is it okay? Similarly, you can go for ket psi can be written in terms of bra psi taking the complex conjugate. So 1, 1 minus 2. Is it okay? 1, 1 minus 2. So psi 1 with psi 2 we are going to find out. What is bra psi 1? Bra psi 1 is 1, 2, 3. Psi 2 is 1, 1 minus. So 1, 1 minus 2i. Okay. You have 1, 1, 2i. So there's a mistake here. 1, 1, 2i. It must be 1, 1, 2i. So you have 1, 1, 2i. Multiplying these two, that will give you, using matrix multiplication, you will have 3 plus 6i. Now if you want to calculate psi 2 with psi 1, here psi 1 with psi 2, you want to calculate psi 2 with psi 1, take the complex conjugate, you will get the answer. You just take the complex conjugate of this one, you will get 3 minus 6i. Is it okay? This is another idea. Or otherwise you will go with the regular operation with, you will have to take psi 2 and psi 1, do the operation exactly like this and get the answer. You will get the same answer. Okay. So complex relation for the basis vector is given by, this is put together, we can write this as inner product psi with psi, that will give you psi star psi d tau, which is equal to mod psi square d tau, and this value must be greater than or equal to 0 always. So we have taken the modulus squared and we have integrated. So this function is known as square integrable function. So very important concept in quantum mechanics. So we have to choose the wave function in such a way that if you take this answer must be less than infinity. It must be greater than 0. Okay, it must be greater than 0 or equal to 0 or less than infinity. This is called square integrable function. Okay, and just now we have seen inner product. Okay, inner product is like this. So this is one inner product. Okay, inner product will give you always a number. I dot I will give you a number. Okay, I dot I will give you a number. Okay, similarly here we are going to do on the other way around. Here it is bra with ket. Here ket with bra. Ket with bra will give you identity unit operator, identity one. So unit operator. So this is called outer product. Sometimes we call this as a projection operator. For example, if you take the similar problem, you will take 112i, that will give you 12i. So this is 112i, this will be 123i. Suppose if it is like this, then we will have the answer, final answer exactly like this. So this is an operator. Look at this one. We have, as I said, this is inner product which will give you a number, whereas the outer product that will give you an operator. Very, very important. Okay, an operator. And another important one conclusion is trace of the outer product is the inner product. What is the meaning of trace? Trace is the sum of diagonal elements. So you wrote a sum of diagonal elements. So trace of outer product will be always the inner product. So this is also very important conclusion. You can try for any other. Trace of outer product will be always the inner product. So here, as I said, I is a unit vector. When the unit vector acts on any ket, it leaves the ket unchanged. This is the unit vector. Unit vector operates on psi, will give you psi. The same. So that's why we can write that when the unit vector, unit operator acts on any ket, it leaves the ket unchanged. So I unit operator operates on the wave function, will give you psi. So I can be written as with the outer product like this, correct? I can write I exactly like this. This psi is here. This ket psi is here. Instead of I vector, I can write this. Is it okay? Okay. Now you just take these two. So these two, that is brass ion with psi. Brass ion and psi is an inner product. It's a number. Understand the concept clearly. Brass ion and psi is a number. This is inner product, correct? So inner product is a number I can take anywhere because it's a number. Suppose if it is 5x, I can write xy also. Doesn't matter. So it's a number. I can bring the number anywhere. So similarly, psi and psi is an inner product. I can bring this term front. So I can write like this. Is it okay? And as I said, this is a number, correct? So number can be represented in terms of Cn. So Cn equal to psi n psi. Cn equals psi n with psi. Okay, and this is, and Cn is nothing but the expansion coefficient, and this is the projection operator which represents the projection of psi on psi n. What does it mean? Psi is the initial one, psi n is the final one. Projection operator means it will project on the basis or subspaces. Okay, it will project. It can project any vector on the basis. Okay, on its own basis. So which represents the projection of psi on psi. So generally we can write the inner product as psi I, psi j, which is nothing but del ij. Okay. Suppose if it I equals j, we can write psi I with psi I, that will give you 1. If it is not equal to j, this becomes 0. So this represents the inner products, inner product, both are inner products, and this represents the normalization and this represents the orthogonal. So here delta ij is nothing but Kronecker delta function, okay, which we have studied already in mathematics. So psi a and psi j are orthonormal vectors. So linear vector space generally it can have some, it has to have some properties. It has to have some properties, especially addition and multiplication, which we are going to see now. So before that, and of course we know vector is a physical quantity having both magnitude and direction. We know already. The vector of magnitude is called a unit vector, which represents an arbitrary vector. We know already. Okay. Suppose if we consider 3 dimension. Okay, 3D, real space. I, j, k are both are mutually perpendicular to each other, and they are nothing but basis of 3 vectors. So they are basis. Any vector y can be represented in terms of this expression c1i plus c2j plus c3k. I, j, k are basis vectors. C1, C2, C3 are unit vectors, or otherwise coefficients we can say. So they are all unit vectors, and they form a basis. Okay, in 3D. Suppose if we go for n dimension space, n dimension space. So this can be written in terms of n dimension as y1 e1 cap, y2 e2 cap, dot dot dot, yn en cap. So we can write this as yi ei, okay, with a summation. And e1 e2 e3 are bases in n dimension. Here I, j, k are 3 bases in 3 dimension. Okay, here n dimension. So this is the difference between these two. Since these unit vectors are mutually perpendicular directions, we say that I, j, k, they form orthogonal bases. And as I said, C1, C2, C3 are coefficient and scalars, and their components are I, j, k. They form a basis vectors. We can represent in terms of matrices also. The same vector can be represented in terms of matrices as y equal to y1, y2, y3, 3 dimension. This is for the n dimension. Okay, we can differentiate. The components of I are, suppose we have components of I are, the first letter will be 1, other things and all elements will be 0, 0. Similarly for j, the second element exists, so 0, 1, 0. For k, third element exists, so 0, 0, 1. So they are all basis vectors which are written in terms of column vectors. So I can be written as in terms of matrices 1, 0, 0, 0, 1, 0, k can be written as 0, 0, 1. Okay, now we will go with the properties of vector space. Few properties it has to oblige. So operations on two vectors in Rn. Rn is real space. Okay, suppose we consider two vectors. This vector consists of many components u1, u2, dot 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 un. This vector consists of many components v1, v2, v3. Suppose. Then these two vectors are equal, provided these two components must be equal. Okay, if the components are equal, we can say that these two vectors are equal. Okay, if the components are equal, u1 equals v1, u2 equals v2, un equals vn, then we can say that these two vectors are equal. Vector addition. So you can add each components into other vectors. Okay, suppose u plus v can be written as u1 plus v1, u2 plus v2, dot dot dot, un plus v1. So you can add the components and get the vector addition. So this can be represented in terms of matrices. Okay, u plus v. So this is represented in terms of matrix u vector, and this is v vector. You are going to add these two, that will give you the final one, u plus v. Similarly, difference, subtraction, u minus v. So each component in each vector will be subtracted. So this is the way. u1 minus v1, comma u2 minus v2, u3 minus v3, dot dot dot, un minus v1. Scalar multiplication, very important one. Scalar multiplication, we are going to multiply any vector with any scalar, that will give you this expression, cu1, comma cu2, dot dot dot, cun. In terms of matrices, we can write exactly like this. So c is a scalar, u is a vector. In terms of matrix, this can be represented in terms of matrix. So c multiplied by matrix, that will give you the last one, cu1 column vector, cu2, cu3. Okay, zero vector. So zero vector can be written like this. So this is called additive identity for the addition. Okay, negative one. Negative is you just go with all negative sign. So this is additive inverse. So inverse of u in terms of addition. Okay, vector addition and scalar multiplication are very important concepts in linear vector space. Vector addition and scalar multiplication. So this is scalar multiplication. Earlier we looked into vector addition. Okay, now properties of linear vector space. So some properties exist. Let V be a set on which two operations, as I said, vector addition and scalar multiplications are very important in linear vector space. If the following axioms are satisfied for every u and v and w. Suppose we take u, v, w in vector space, linear vector space, we will have some scalars c and d. So we are going to take scalars c and d, vectors u, v, w in linear vector space. Then vector addition, u plus v. So you have u, you have v, you are going to add these two. The result also will belong to linear vector space. The resultant will be in union vector space. So this is called closure under addition. Okay, similarly u plus v equals v plus u. If we add these two and interchange, again final answer will be the same. This is called commutative property. So next one is associative property. Okay, so u plus v plus w will be equal to u plus v plus w. This is associative property. U plus 0 equals 0. Okay, so when you are going to have identity element, if you are going to add, you will get the same. And this is inverse property in addition. U plus minus u will give you 0 vector. Now we will go for scalar multiplication. C multiplied by u, if you are going to multiply any vector with any scalar, the answer also will belong to linear vector space. This is called closure under scalar multiplication. So any scalar, if it is multiplied with u plus v, that can be written as cu plus c. Okay, this is very very important concept in quantum mechanics, scalar multiplication. Okay, so suppose if we consider instead of scalar, we consider any operator. Instead of scalar, we are going to have an operator. Operator operates on the combined system is equal to sum of the operation of the individual system. Is it okay? See, instead of C, you just go with some other operation. Okay, operators operate on the combined system is equal to sum of operation on the individual system. It's a very very important concept in quantum mechanics. Okay, this is scalar multiplication. Suppose if you have instead of two vectors, if you have two scalars, c plus d, okay, and acting on any vector, so individually you can write. So this is distributive property. Okay, and if you have c du, that will give you just together you can multiply. So cd multiplied by d. So cd acts on u vector. You can have identity. Multiplication identity will be 1. So 1 multiplied by any vector will give you the same vector. Examples. These two are very very important, as I said, in linear vector space. This is called a vector addition. This is called a scalar multiplication. So any matrices you can have a vector addition. Vector addition is nothing but you are going to add each element. So u11 plus v11. Similarly u12 plus v12, u21 plus v21, u22 plus v22. Okay, this is vector addition. Scalar multiplication, k multiplied by each number, that will give you scalar multiplication. So these two are very very important in linear vector space. One is vector addition, another one is scalar multiplication. Now next concept will be linear combination. So any vector can be written in terms of linear combination of vectors. Okay, any total system can be written in terms of linear combination of individual vectors. So this is termed as like this. For example, v equals c1 u1 plus c2 u2 dot 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 ck uk or cn un. So these are all linear combination of vectors. The operations are linear. Okay, operations are linear. Transformation. Suppose if you have a quantum system, you are going to measure the quantum system. Quantum system will occupy in any one of the place. Suppose for example, we have 3 chairs. So we have already said this example, we have 3 chairs. I am going to ask you anyone to occupy 1 chair. So you will occupy only 1 chair. But the electron will occupy all the 3 chairs with a linear combination. Suppose you are going to measure the electron where it is, and you can find only the electron will transform from one chair to another chair after the measurement. It will occupy only 1 chair. This transformation from one chair to another chair is nothing but linear transformation. Okay, so this is called linear. We will look into linear later. So this is linear combination. Okay, and c1 c2 are scalars. Now we will go for example 1. Suppose S equals 1 3 1, 3 vectors 0 1 2, 1 0 minus 5. So we will consider this as v1, we will consider this as v2, we we'll go with V3. This is V3. Then we can say that you just take 3V2, 3 times V2 plus 1 times V3, only 1 time V3. You add these two, that will give you 131, which is nothing but V1. So V1 can be thought of as 3V2 plus V3. So linear combination of these two will give the rest of the one. So it's a dependent vector. Okay, this is for the example. Now next concept will be span and basis. Of course, basis we said basis is nothing but ijk. This is not a basis. For example, just now we said u1, u2, u3, they are all basis vectors. Like ijk, we have 3 dimensions, three bases. So similarly, u1, u2 are basis vectors. Okay, now we'll go for span. Gilbert space is spanned by basis vectors. Gilbert space is spanned by basis vectors. It's a very important concept. Suppose if we consider S having some components, say v1, v2, vk, be a subset of in vector space, we'll consider. Then the set S is called a spanning set of V. So S is a spanning set of V. Gilbert space is spanned by basis. Just now I said. So every vector in V can be written as a linear combination of vector in S. In such cases, it is said that S spans V. S spans V. Okay, S is a subset in V. So S spans V. For example, you take S. There are 3 vectors 1, 0, 0, 0, 1, 0, 0, 0, 0. For example, then R3, we can write R3 in terms of U like this. U equals U1, 1, 0, 0 plus U2, 0, 1, 0 plus U3, 0, 0, 1, which is nothing but U1, U2, U3. Okay, so basis is, as I said, ijk. So they are all bases. So S equals, suppose we consider any vector S equals v1, v2, vk in vector space. Then V is called a basis for V if the following conditions are true. So S spans V. S is linearly independent. The standard basis for R3 will be one vector, second vector, and third vector. See, for example, just take ijk. I can be written as 1, 0, 0. J can be written as 0, 1, 0. K can be written as 0, 0, 1. So 3 dimension. So 3 dimension means 3 bases. If you go for 4 bases. So 4 bases can be written as in terms of rows 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So 0, 0, 0, 1. So this is 4 bases. So similarly, we can go for n dimension. N dimension is something like this. Okay, all these basis vectors can also be written as column vectors. We have written row vectors, correct? So they are all row vectors, and they can be also written in terms of column vectors. This column matrix notation is frequently used in quantum mechanics. So we always use quantum mechanics often. So for example, just take column vectors. So just take column vector, I can be written as 1, 0, J can be written as 0, 1. So this is exactly like a spin state. So spin state, up and down. Okay, spin state, up and down. So this can be written as 1, 0, 0, 1. So if R equals xi plus yj, that can be written as R equals x into 1, 0 in terms of column. See, like this, which you have written earlier. So similarly like this. Similarly, 1, 0 plus y, 0, 1. If you add these two, that will give you xy. So for 3 dimension, 1, 0, 0 in terms of column vector, j equals 0, 1, 0, k equals 0, 0, 0, 0, 1. So if you are going to do this operation, you will get this expression. So R equals x, y, z in terms of column vector. So we can write in terms, we can plot in terms of this ijk can be plotted here. Now what are the properties? Addition is commutative and is written as a plus b equals b plus c. Some properties exist for linear vector space. A plus b equals b plus b. Then associative property will be a plus b plus c equals a plus b plus c. The product of two vectors a, b operates on f of x will give you a, b operates on f of x. Multiplication is associative. that is AB plus C, AB with AC operates on any function f of x. Then commutative of operators A and B denoted as A comma B equals AB minus BA. Very, very important concept in quantum mechanics, commutative property. A comma B with this bracket. So this bracket is called commutative property, which is equal to AB minus BA. Suppose if A comma B equals 0, it implies that it's said to commute with each other. If answer is 0, that means it will commute with each other. That means simultaneously you can measure. Simultaneously you can measure. Suppose one operator is there, another operator, you are going to make the commutator with these two operators. The answer is 0. It implies that both operators can be measured simultaneously. If it is not equal to 0, if you have some value, they can't be measured. So this is a fundamental one in quantum mechanics. So this is A comma B is commutative. Suppose if you have A instead of AB minus BA, if you have AB plus BA, which is equal to 0, this is called anti-commute. So one is commute, another one is anti-commute. It implies that the operators A and B are said to have anti-commute with each other. So anti-commute. If it is plus, anti-commute. If it is minus, commute. Okay. So these two properties are very important. We'll be using often in problems. So we'll go for A inverse. So A inverse, which is equal to A inverse A, which is equal to I. Okay, unit operator.